Okay guys, please turn to page 474, problem 9.9. If you can read from the questions, we are given a conducting rod which one end grounded at the origin and then the other end is free to move around the z-axis within the static B field given as 60 millitesla in z directions. Okay, so now let's say this we pick at this particular position at certain angle, let's say, and then the angle here actually can be related to the omega, which equal to the omega t. Okay guys, so the rod has a length of 8 centimeter, labeled as A, and then let's define the edge here is edge number 1, our first terminal, and then here is our second terminal. Let's define ourselves. Now I'm going to calculate the EMF induced in the rod. So again, since we are dealing with a movement of rod and the B given here is a static B field, so for sure it is a case of motional EMF. Okay, so let's recall our equations of motional EMF. EMF is equal to closed integrations U cross B dot dl. Okay, so now we assume that the rod rotates in counterclockwise direction as shown here. Okay, that's our own assumptions. Okay, now since we do have already the B field given as B dot Z, but we don't have yet the U here. We only have the omega given, so we have to relate or convert the U here in terms of the omega. So if you can recall our knowledge on the equation that relates between linear velocity with the angular velocity, those parameters can be related using these equations. The U, our linear velocity, is equal to the r, the radius, omega phi directions. So that's the general equations which relates between the linear and angular velocity. So now we do have already the U and B, so let's substitute U and B inside these equations. Now we have close integrations U. Now we have R omega phi directions cross the B naught Z, which the B naught now is equal to 60 milli. Okay, and dot dl. So now how do I know the dl? So just look at to the rod where it is being placed. Now guys, you can see that the rod actually is placed along the R directions or R axis. So now we can simply put here R dr for the dl. Okay, so now let's perform the cross product between the phi component and the z component here. So now we are going to have the positive R directions or component. So now next step, how do I know the limit for these integrations? Again, it can be determined by looking at the current flow, and the current flows can be determined by the cross product between U and B. Okay, let's choose these particular positions of the rod at this certain time. So we have to find the U at this particular point. Okay, so let's look at this equation, guys. The U is equal to R omega phi. So the U is actually the U that appear at this tangential point of the road. So if you want to draw the U, you can see from here the U direction actually is in that directions. That's the U, which 90 degree with the road. Okay, so that's the U, guys. And then we also have the B already in Z. So now by looking at these particular positions at certain theta, right? So the U, again using our right hand rule, the U is the rest fingers, shows that way, that directions, and then the B flow pointing upwards in positive Z directions. So let's look at your thumb fingers. So now refers to the current flow, which pointing along this direction, is it, from first terminal to the second terminal. So that's going to be our I directions if it has a complete circuit. Okay, so now we can set the limit for this integral from first terminal to the second terminal, which is from 0 until the length of the road A. Alright, so now let's proceed. We have here the B0 omega. Let's take out the constant, and then let's deal with the integrations over dr 0A. Now we have r dr. So if you form the integrations, we have here half B0 omega A squared volts. Okay, so let's substitute all the value of B0 omega and A. So the EMF here, we have half, the B0 is equal to 60 milli, and then the omega is equal to 30 radian per second, and also the length of the road given as 8 centimeter. Okay, which will give us the value of 5.76 millivolt. Okay guys, so since we know that the current will flow from terminal 1 to terminal 2, we can simply say that at this terminal 1 it actually at lower potential. Meanwhile, at this terminal 2, it has, or it at higher potential, and then the EMF that we obtain here actually refers to the polarity, the positive and negative, and that is going to be the EMF that we obtain down here. Okay, so I hope you can follow me and you learn something. So please redo, and all the best for your revisions. Thank you.